Hello and welcome to another power electronics class. In the previous class, we spoke about DC to AC inverters. We continued with three-phase DC to AC inverters. And we mentioned that we have two types of three-phase inverters. We have the ones with the 180-degree delay and the 120-degree delay. We already spoke with the 180-degree delay or the 180-degree conduction mode. And in this method, three of the switches are connected at the same time. And at each 60-degree state, three switches conducts together. So 3 times 60 degrees, 180 degrees. So at 180 degrees, we have conduction and then a delay and then conduction again. In this example, T1, T5, T3, so T1, T5, T6 are connected, and we solved it for its output voltage, and we measured the output voltage. We also mentioned that in these systems, because we have induction, usually we have an induction motor or inductive load, we would have a shift in the current as well, a little bit of delay in the current as well. And this picture here shows the voltage and also the current and the current delayed by theta. Now today we're going to continue with the 120-degree conduction mode, and also we will continue with multi-step inverters. So in the 120-degree conduction mode, each switch will conduct for 120 degrees. In each 60-degree state, two switches conduct together, one connected to the positive terminal and the other one connected to the negative terminal. The equivalent circuit of inverter for each state can be obtained as follows. So in the previous one, in the 180-degree conduction mode, we had T1, T5, and T6 connected at the same time. And T3, T4, and T2 were disconnected. Here we only have T1 and T6 connected, okay? And if I have T1 and T6 connected, then if I draw a loop from V positive Vs to negative, it's going to go through T1, this R, coming back through this R, and you can see that it's going through the negative side. So going through two R's technically, and N is the neutral point that we have here. So can you tell me by looking at it, which one do you think would have a higher voltage, the 180-degree conduction mode or the 120-degree conduction mode? So as you remember, for the 180-degree, T1, T6, and T5 were connected. So I had three sources connected to the load, three switches connected to the load and the source. But here in the 120-degree, we would have only two of them. So let's find the answer for this. So if you want to find, first of all, the switching is going to look like this. The previous time we had each switch conducting for 180 degrees, so 360 degrees. This time we have each switch conducting for 120 degrees, so 260 degrees. So first T1 turns on. After 60 degrees, T2 comes in. And then after that, T1 is turned off. T3 turns on, and we still have T2. And then T2 turns off. T3 continues. T4 kicks in. T4 continues. T3 turns off. T5 kicks in. And then the cycle just repeats. So you can see that T1 turns off. After 180 degrees, it again turns on after it completely turns off. So you can see that the 120 degree, the pulses are further apart compared to the 180 degree conduction mode. And also at the same time, only 2 switches are turned on instead of 3. Now, what happens when the switches are turned on? When T1 is turned on using the Ohm's law in the voltage divider, the voltage over this R, if we find the voltage VR is going to be equal to R times Vs over R1 plus R2, or 2R. So the voltage that we're going to have here, assuming these two R's are identical, the same resistors, it's going to be half of the total voltage. It's going to be divided between 2 equal resistors. So what we have here between Vs and N is going to be half the voltage, Vs over 2. So we have Vs over 2. And then when, and by the way, this is Vrn. Then we have Vyn, Vbn, Vry, Vy by Vyb. So these are the ones that are between the phase and the neutral are the phase voltages, and the ones that are between 2 different phases are the line voltage. So you can see that what happens in the line voltage, for example, Vyb, is the summation of all the voltages that we have. So summation of Vyn and Vbn, for example. And by adding those, you can see that we create a step voltage that is closer to a sine wave compared to the square voltage. Okay? So if you add, for example, T1 voltage, we're going to have Vs over 2. Then at Vrn, then at Vyn, we're going to have negative, and so on and so forth. So by adding these, again, we're going to have this voltage at Vry and Vyb. Do I keep saying what you? So the line output voltage can be obtained as follows. We already did it for the phase. So in a 180 degree mode of a 3-phase inverter, V line RMS is going to be Vs times square root of 2 over 3. And for 120 degrees mode, it's going to be Vs over square root of 2. So just by looking at this, which one has a higher voltage? Which one has a higher line RMS voltage? Obviously, the 180 degree. That one is going to be Vs over square root of 2, or Vs over 1.4. This one is Vs times, and it's going to be a little bit larger if you just calculate them. And the reason is obvious, because that is conducting more compared to the 120 degrees phase mode. What about the V phase? Again, V phase for this one is going to be square root of 2, which is 1.4 times Vs over 3. The other one is going to be little less. Let's find the exact numbers, actually. Let me calculate the exact numbers. Yes. So imagine, let's do a small example. So we want to find V line RMS for the 180 degree mode of a 3-phase inverter and the 120 mode. And Vs is 200 volts. I want you to find V line, V phase for both of them. Okay, did you get the results? So what is V line for the first one? So V line for the first one is going to be 200 times square root of 2 over 3. It's going to be 163. Yes, 63.3. Yes, same thing that I got. What about the second one? V line for 120. Perfect, yes. It's going to be 200 divided square root of 2, which is going to be 141.4. Perfect. So which one is greater? Obviously, yes. And it's greater by about 10%, about 10, 12%. What about the V phase RMS? 94.2 for the 180 degrees. And how much is it for? How much? 81.6. Thank you. And we can find the harmonics here, and the fundamental V1 RMS for 180 degrees is 0.77 or around 0.8 of Vs. And for the 120 degrees mode, it's about around 0.7 or 0.67 to be accurate of Vs. So the output voltage for both the line, the phase, and the fundamental voltage, which is the closest voltage that we can get to the sinusoid voltage, desirable sinusoid voltage, is going to be, for the 180 degrees, it's going to be greater than the 120 degrees. So what happens to the rest? It actually weights. So 180 degree is obviously better, but it's a little bit more complicated than the 120 degrees method. Now, this is an interesting comparison, and I want you to understand this table because you're going to have questions from this on your exam as well. This is a comparison between the 120 and 180 degree conduction modes for three-phase DC-AC converters. So on the first column, you see the parameter. Second column is the 180 degree mode, and the third column is the 120 mode. And for the 180 degree mode, the conduction of the device, each device conducts for 180 degrees. For 120 degree mode, it conducts for 120 degrees. For 180 degree mode, we have 3 devices conduct in one interval. For 120 degrees, we have 2. That one, we had 3 switches conducting, T1, T5, and T6, for example. This one, we had only 2 of them, T1 and T6. The voltage line voltage is the Quasi square wave with plus negative Vs. For the 120 mode, we have 6 steps waveform with plus Vs, plus negative Vs, and plus negative Vs over 2. The phase voltage we have for 180 degree, we have 6-step waveform. Again, these all come from here, the number of steps that we have. So we have 1, 2, you can see 1, 2, 3, 4 steps that we have in this one. And for the other one, you can see we have 1, 2, 3, 4, 5, 6 steps, for example. So you can count the number of steps that we have. So the phase voltage, we have 6-step waveform with positive negative 2 Vs over 3 and positive negative Vs over 3. And for the 120 degree, we have Quasi square wave with positive negative Vs over 2. The possibility of cross conduction, which is actually a dangerous thing. The first one is for 180 degree is possible because the switches are very close together. You may have 2 switches conducting at the same time that we don't want. And for 120 degree, it's not possible. The utilization of the device, the device is better utilized. Obviously, we have higher efficiency and higher output. The signal looks closer to the original signal, the fundamental that we want, a sinusoid output. And the second one, the 120 degrees, the device is underutilized. The output power is higher for the 180-degree conduction mode, and it's less because of the lower voltage levels. And VRMS is for the 180 degrees, as you saw, it's Vs times square root of 2 or 3. And the 120 mode is Vs over square root of 2. So as you can see, the voltage of the fundamental voltage of the 180 degree is greater than 120 degree. Now I've put an example here. On the exam, you may have the same example, and I'll post some homeworks on this. The only thing you need to do is just replace the numbers, and it's going to be pretty straightforward. So it's going to be similar to the previous example that we have. We have a three-phase inverter. It has a Y-connected resistive load of 10 ohms. The inverter frequency is 60 hertz. The source voltage is 220 volts. And we want to find the instantaneous line-to-line voltage, line to current, and line current. In a Fourier series, we want to determine the RMS line voltage, VL, RMS phase voltage, and line voltage at the fundamental frequency, VL1, RMS phase voltage at the fundamental frequency, VP1, total harmonic distortion, THD, distortion factor, DF, harmonic factor and distortion factor of the lowest order harmonics, load power, Pout, average transistor current, ID, and RMS transistor current, IR. So first thing we want to do, we want to find the instantaneous line-to-line voltage. And we can do that using this equation, which technically is the Fourier series for it. And writing that, the phase voltage, as we know, is going to be the line over square root of 3 because of this is a Y connection or a star connection, sometimes they say, with a delay of 30 degrees. Therefore, what we do is we just subtract that phase from it, and the amplitude would be divided by square root of 3. This gives us the current. So it's going to be the same divided. If I want to find the voltage of the phase, it's going to be the amplitude divided by square root of 3 minus the phase. Now, you can use the Ohm's law. I is equal to V over R. And we know that R is 10 ohms. So first you can find the phase voltage, and from that you can find the phase current. And again, the phase voltage is going to be VAB divided by square root of 3 with a 30-degree delay that we have. And therefore, the phase current is calculated. The line voltage, again, we can find the line voltage by combining all these, the Fourier series that we have, and it's going to give us 179.63. Doing this manually is going to be difficult. You're not going to have a question like this on your exam. We usually do this with Simulink, MATLAB Simulink. It's going to be much easier doing it right with that. But you need to probably measure the total harmonic distortion and the distortion factor. And V phase is going to be 103.7, and the fundamental line voltage is going to be 171.53. There is a difference between the fundamental line voltage and the line voltage, and this is basically the harmonics that are adding to the signal, which are undesirable. And that is actually our total harmonic distortion that we and the harmonic distortion that we have. So the fundamental phase voltage is going to be the fundamental line voltage divided by square root of 3, because it's a Y connection. It's going to give us 99.03. And VL1 is going to be 0.7797 Vs. Where did we get this number? VL1 is 0.7797 of Vs. Because this is in a 180-degree conduction mode, this is where we got this equation from. In a 180-degree conduction mode, VL1 is going to be 0.7797 of Vs. Now we can find the total harmonic distortion using the VL square minus VL1 square. Square root of that gives us 0.2436 Vs, and total harmonic distortion is going to be 0.24236 Vs over 0.7797 Vs, which gives us 31.8%. And therefore, we can find total harmonic distortion. Now, the distortion factor will be the total harmonic distortion divided by VL1, which gives us 0.00668 Vs over 0.7797 Vs, which gives us 0.857%. The lowest order harmonic is the fifth here, which is VL1 over 5. We already have VL1, and we can find VL5 over VL1, which is going to be 20% of the amplitude of VL1. And the distortion factor for the fifth harmonic is going to be equal to VL5 over 5 square, which gives us 0.8%. By the way, this is the harmonic factor, not to mention. What else are they asking for? Average transistor current and RMS transistor current. So the lowest order harmonic, we already found it. For Y connection loads, the line current is the same as the phase current, and the RMS line current, IL, would be I phase over 10, Ohm's law, gives us 10.37 amps. The load power is going to be 3 V phase I phase, which gives us 3,226.4 watts or 3.2 kilowatts. The average supply current would be P is going to be equal to VI, therefore I is equal to P over V for each phase, and it's going to give us 14.67 amps. And the average transistor current, ID, would be equal to that current divided by 3, because we have 3 phases coming in. It gives us 4.89. Since the line current is shared by 2 transistors, the RMS value of the transistor current will be ILO with square root of 2, which gives us 7.33 amps. Now, another way to have a clean output signal, something that is very similar to a sine wave, is to use multi-level inverters. So square inverters have this limitation of creating harmonics. Why? Because we are suddenly, again, moving from positive to negative to positive. And what we want, actually, the desired signal is something like this, but what we are getting is a square signal. And the limitation for this, as mentioned, we can solve it using some filters. that's a good way. Another way was to be able to, for example, use different conduction modes and to use pulse width modulation for that. But a different approach to this is, instead of having just two stages of signal being on and off, what if I divide that input voltage to multi-levels? Imagine if I put that 220 voltage into a voltage divider, then I have a 120 volts. Now I have one stage that is 120 volts. Then I have another one that is 220 volts, for example. So now what I have, let's say, make this part. Now what I have is something that is closer to the sine wave. So here I have two different levels. What if I have four different levels of voltage? So I'm going to draw this one with green. Now I can have something that looks like this. So more levels that I have, I'm going to have a cleaner output and something that is closer to a sine wave. Okay, if I boost that to infinity, I'm going to have a clean sine wave. Obviously, you can't do that. So another way to have a pure sine wave output in an inverter is to have multi-level inverters, meaning at each level, the switch connects the output to a different input voltage. So to reduce the effects of inverter harmonics and to increase the RMS AC output voltage, multi-level inverters can be used. These multi-level output voltages are more sine-like in quality and thus reduce the harmonic content. The multi-level inverter is suitable for applications including adjustable speed motor drives and interfacing renewable energy sources such as solar and wind. And the reason it's very important actually in solar wind, because when you're running a motor, if you produce a signal that it's somewhat sine wave, okay, if I create something that looks like this, and this is connecting, imagine I've created a signal that looks like this, close to, sine wave, but not actually sine wave. And I connect this to a motor that it's a pump and it's pumping for me. So I imagine you put a solar panel in a field, it's a remote field, and you're using that solar panel to just pump water during the day. If the inverter looks like this, the motor is going to run. You may, damage the motor after a few months or a year if it's a bad inverter, but the cost is just wiring of a motor, and probably the first thing that blows up is the capacitor, the compensation capacitors. So you're damaging one motor. But what if you have a solar farm, a wind farm, and you want to connect that to the grid? Okay, if you have an inverter that looks like this is going to damage the whole transmission line and the grid and the system, which the cost is way higher. Even if the frequency is like 1 hertz, the frequency must be perfect, synchronized. Okay, voltage must be perfect, the frequency must be perfect. So phase, voltage, frequency, all of them must be, and the shape of the signal, obviously. Creating harmonics is going to heat up the transmission lines. It's going to cause a lot of damage. So for those that we need a very clean signal, multi-level is the way to go. So this shows a multi-level converter with independent DC sources. So one multi-level inverter method uses independent DC sources, each with an H bridge. So for example, this one creates, let's say, 100 volts, and the other one creates 120 volts. Now the total voltage that we're going to have here is going to be VO1 plus VO2. So for example, here it's going to be 100 plus 120 gives us 220 volts. Now instead of 2, what if I have 3, another one here, you know, and then I could divide the 220 volts to, you know, 60, 60, and 100, okay? Then I would have, instead of having 2 levels, I would have 3 levels, for example, of voltage. So the more of these I have more levels. So this is, for example, for a 2 level, and this would be one which has 4 independent, for example, voltages, 3, 4, and the higher we go. So for example, if we have like 8 or 9, let me do one with more levels. So imagine that I have one that it's 8 level like this. So the higher the voltage sources are, we're going to create a signal that looks better, cleaner, closer to the fundamental with less harmonics. How can we build the system? If you have a solar system, one way is to divide it. So you know that solar panels, we can connect them in parallel and series. You can connect them in a way that one string produces 100 volts, the other one 120, and so on. Or you can divide it to 10 different, you know, batches, and each batch, you know, produces 22 volts. Then you would have 10 levels of that. Okay, that's not a good way, and there are multiple reasons. I'm not going to go deep into that, but we have other ways to do that. But this is one way to do it. The reason that we don't want to do that, because if one batch is shut down or we have a shadow on it, it's gonna completely put the thing out of balance. Another way that we can do this is that we can use variable buck-boost converters at the inputs. So we can have a source voltage which is DC, you know, at 800 volts. Then we can have buck converters connecting and reducing to 100, 120, 130 different levels of voltages. And for wind, we can do that as well. We can convert it first to DC with different levels of voltage. Like one output is 200, one output is 100, one output is 300, something like that. And then you can have these multi-level inverters at the output. Now the signal for them, it's going to look like this. V1 is going to look like the one at the bottom. V2 is the middle one, and V out would be the upper one. So V1, we can start the conduction at alpha 1 and stop at P minus alpha 1. And V2, we can start at alpha 2 and P minus alpha 2. And then we can have the outputs. Now, why did we do alpha 1 and alpha 2? We can, as I mentioned, use a multi or variable DC source that uses a buck boost converter. And the way that we can control the buck boost converter's output is by controlling its width, pulse width modulation. So the first one has a higher width. The first one has a smaller width. Okay, so by adjusting these, what we call firing points, alphas, and start points, we can create different voltages. So again, instead of having different voltages, another way is using buck boost variable converter, and therefore we can have different outputs. And if we solve it, V out T is going to be 4 VDC over pi, the sigma of that, the output signal, which is again using Fourier series, and Vn would be 4 VDC over n pi, cosine of n phi 1 plus cosine of n phi 2. And by adjusting phi 1 and phi 2, we can adjust the levels of the voltage and therefore the output voltage for the nth harmonic. So for example, for the two multi-level inverters with a VDC of 100 volts, we want to determine the Fourier coefficient through n equal to 9. So for the 9th harmonic, for alpha 1 equal to 20 degrees and alpha 2 equal to 40 degrees. Determine alpha 1 and alpha 2 such that the 3rd harmonic n equal to 3 N3 is eliminated. So to evaluate the Fourier coefficient, we would write the Fourier series equation. And from this, by replacing n with the fundamental, which is the 1, 3rd, 5th, 7th, and 9th, we can find each harmonic magnitude. So V1, if we solve it, it's going to be 217 volts. V3 is 0. V5 is negative 28.4. V7 is negative 10.8. And V9 is 0. Note that the 3rd and 9th harmonic are eliminated. The even harmonics are not present. As we know, we don't have even harmonics. Therefore, cosine of 351 plus cosine of 352 would be equal to 0. To achieve the elimination of the 3rd harmonic requires the solution to the equation for this part. We need to be 0. So therefore, Vn is 0. Using an iterative method, we can find alpha 1 is going to be 7.6 and alpha 2 is 52.4. So the good thing about this multi-level system is we can selectively eliminate the harmonics that we don't want. And usually the harmonics that we don't want are the 3rd, 5th are the most destructive harmonics. After the 5th, usually they are not a big concern for us. Now, the preceding concept can be extended to a multi-level converter having several DC sources. So for example, here we have 5 DC sources. Therefore, we can have 5 different levels of voltages, positive and their negative, so 10 in total. So for K separate source connected in cascade, there are 2K possible voltage levels. As more DC sources and H bridges are added, the total output voltage has more steps, producing a staircase waveform that more closely approaches a sinusoid. For a 5-source system, as shown in the figure below, there are 11 possible output voltage levels. So you have 5 positive, 5 negatives, and the 0 as well. So you can see this is different alphas for V1, V2, V3, V4, and V5 from bottom to top. V1 has the highest alpha, and then V2, and then V3, and up to V5. Now, by controlling these alphas, we can control the output voltage in each level. But more levels that we have, we're going to have a cleaner signal, something closer to sinusoid. So we had this one, which was only 2 levels. You can see it's not very close to the sinusoid. If we connect them, it's going to look somewhat like if we have a capacitor, it's going to look something like this. This one, it's going to look much smoother and closer. Now, this is the reason these pure sine wave inverters that use this method are very expensive. You need, instead of having just 1 or 2 bridge, you need multiple bridges. You need multiple filters. So it's technically 10 times the material that you're going to have for a square wave. And if one of them goes wrong, the whole system is going to fail. So you need to make it durable. You need to have very big heat sinks. That's the reason that the cost is sometimes 10 times a square inverter. Square inverter is simple switch on and off. So this is a square wave, 5-source cascade multi-level converter, and equalizing average source power with pattern swapping, we get this. In the 2-source inverter, the source and H bridge producing the voltage V1 supplies more average power and energy than the source and H bridge producing V2 due to the longer pulse width in both the positive and negative half cycles. If the DC sources are batteries, one battery will discharge faster than the other. A technique known as a pattern swapping or duty swapping equalizes the average power supplied by each DC source. So these, if you have an intelligent system, now you want to connect it to multiple batteries, then you have to have an intelligent system not to drain one battery faster than the other. So as mentioned with the solar panel, we may have that problem. Another application for this is for EVs. EVs usually have battery packs, and then if you divide them and give each one to the input to eliminate the need of multiple, buck boost converters as the input variable, we're going to have the problem of depleting, because at V1, for example, this is getting more energy compared to V2, so you're depleting one battery faster than the other. Then after like 30 seconds, you have to switch the sources. So what I'm seeing, actually, I've seen a lot of these, is they would all skip this and go to just using, a inverter. The inverter would be complicated, but you can use the battery pack as a single battery pack, and then you can have multiple outputs for that using the buck boost variable converter inverters. Okay. I have a short video prepared as well. And I think this is very helpful. This summarizes what we learned so far in a graphical way.
Understand the basics of how they work and where we use them. Remember, electricity is dangerous and can be fatal. You should qualify as competent to carry out any electrical work. A typical inverter looks something like this. It has some red and black DC terminals on the back end, and on the front end we find some AC electrical outlets. That's because there are two types of electricity. There is AC and there is DC. An inverter is used to convert DC, or direct current, into AC alternating current. We can also convert AC into DC with the use of a rectifier, but we'll cover that in a separate video, and I'll leave some links in the video description down below for that. The appliances in our homes are designed to run off of an AC supply, and they get that from the electrical outlets, which all provide AC electricity.
Hi, I'm Bert, a small business insurance expert with Fiverr.
What's a fiber?
Fiverr isn't a thing. Fiverr is a way, the smart way.
However, electricity produced by things such as solar panels and batteries produce DC electricity. So, if we want to power our electrical devices from renewable sources, battery banks, or even our car, then we need to convert DC electricity into AC electricity, and we do that with an inverter. Where have you seen inverters used, or where would you like to use one? Let me know your thoughts and your project ideas in the comment section down below. To understand how an inverter works, we first need to understand some fundamentals of electricity. Inside a copper wire, we find copper atoms. These have electrons which can move to other atoms. These are known as free electrons because they are free to move around. They will randomly move in all directions, but this isn't of any use to us. We need lots of electrons to move in the same direction, and we do that by applying a voltage difference across the wire. The voltage is like pressure and will push the electrons. When we connect a wire to the positive and the negative terminals of a battery, we complete the circuit and electrons begin to flow. We call this flow of electrons current. The electrons always try to get back to their source. So if we place things such as lamps in the path of the electrons, they will have to pass through this, and they will therefore do work for us, such as illuminating this lamp. The electricity from solar panels and batteries is known as DC electricity. And that's because this type of electricity flows in just one single direction. It flows from one terminal directly to the other terminal. If we reverse the battery, the electrons flow in the opposite direction. You can think of DC electricity like a river, with the current of water flowing in just a single direction. Now in these animations, I use electron flow, which is from negative to positive. But you might be used to seeing conventional current, which is from positive to negative. Electron flow is what's actually occurring. Conventional current was the original theory and is still widely taught today. Just be aware of the two and which one we're using. When we use an oscilloscope to look at the electrical waveform for DC, we get this flat line at the maximum voltage in the positive region. If we were to cut the power, then the line will drop to 0. If we turn the power on and off repeatedly, then we get a square wave pattern between 0 and maximum. But if we were to pulse the switch to open and close over different lengths of time, then we would get a pulsating pattern. With AC electricity, the electrons alternate by flowing forwards and backwards constantly. That's how it gets its name, because the current of electrons alternates in direction. You can think of this type of electricity like the tide of the sea. It constantly flows in and out between the maximums of high tide and low tide. If we follow the copper wires back to the generator, the wires are connected to some coils of wire which sit within the generator. Inside a basic generator, we also find a magnet at the center which is rotating. The magnet has a north and south pole, or you can think of it as a positive and a negative half. The electrons in the wire are negatively charged. As you might already know, magnets push or pull depending on the polarity. So as the magnets rotate past the coils, the positive and the negative half are going to therefore push and pull the electrons within the copper coils and also through the connected copper wires. The magnetic field of the magnet varies in intensity. So as the magnet rotates past the coil will experience a change in intensity of the magnetic field. This will be from 0 up to its maximum intensity, and then as it passes the coil, it will decrease again back to 0. Then the negative half comes in and pulls the electrons backwards with the same change in intensity. Each full rotation of the magnet will therefore produce this wave pattern known as a sine wave. The voltage is not constant in this type of electricity. Instead, it repeatedly moves from 0 up to its peak, back to 0, then to the negative peak, and then finally back to 0 again. Frequency refers to how many times this AC sine wave repeats per second. In North America and a few other parts of the world, we find 60 Hz electricity, which means the sine wave repeats 60 times per second. And as each wave has a positive and a negative half, this means its polarity will therefore reverse 120 times per second. In the rest of the world, we mostly find 50 Hz electricity. So the sine wave repeats 50 times per second, and therefore the current reverses 100 times per second. The inverter consists of a number of electronic switches known as IGBTs. The opening and closing of the switches is controlled by a controller. These can open and close super fast in pairs to control the flow of electricity. By controlling the path which the electricity takes,
imagine being able to build an app with your name on it just by thinking about it. Meet Base 44,
a complete and how long it flows in the different paths, we can produce AC electricity from the DC source. I'm going to animate these using some simple switches to make them easier to visualize. Remember, AC is where the current reverses direction. We saw earlier in the video that we can reverse the direction of current by reversing the battery. We could very quickly reverse the battery to produce a rough AC supply. But an easier way would be to connect 4 switches or IGBTs across our load, such as a lamp. If we open and close these in pairs, then we can produce AC electricity. So if we were to close switches 1 and 4, then the current flows in one direction. And if we then open these and close switches 2 and 3, we get current flowing in the other direction. So we can use the controller to automatically do this again and again and again. If we did that 120 times per second, then we would get 60 Hz electricity. And if we did that 100 times per second, then we would get 50 Hz electricity. As we have a low voltage input, we're going to get a low voltage output. To reach the 120 volts or 230 volts required to power our appliances, we will also need a transformer to step up the voltage to a useful level. When we look at this through an oscilloscope, we get a square wave in the positive and the negative regions. This is theoretically AC because it reverses direction. But it doesn't really look much like an AC sine wave. So how can we improve this? Do you remember earlier in the video when I said we can open and close the switch at different speeds and durations to change the waveform? Well, we can do that for this too. What we do is to use a controller to rapidly open and close the switches multiple times per cycle in a pulsating pattern, each pulse varying in width. This is known as pulse width modulation. The cycle is broken up into multiple smaller segments. Each segment has a total amount of current that could flow. But by rapidly pulsating the switches, we control the amount of flow occurring per segment. This will result in an average current per segment, which we see increases and decreases, thus giving us a wave. The load will therefore experience a sine wave. The more segments we have, then the closer it mimics a smooth wave. We can control the output voltage by controlling how long the switches are closed for. So we could, for example, output 240 volts or 120 volts just by trimming the opening and closing times. We can also control the frequency by controlling the timing of the switches. So we could, for example, output 60 Hz, 50 Hz, or 30 Hz, whatever is needed for the application. So that's how we can take a 12-volt DC battery and convert this into a 120 volts or 230 volts AC supply by using some IGBTs, pulse width modulation, and a transformer. But what if we needed more power? We also have single-phase as well as a three-phase AC electricity. Most homes around the world use single-phase electricity. Large commercial buildings, as well as some homes, especially in Europe, will use three-phase electricity. Homes in North America use split-phase electricity, where a center tap transformer splits a single phase into two, which provides two hot wires and a neutral. We've covered how split phase electricity works in detail in our previous video. Please check that out, links down below. With single phase, we have a connection to just a single phase from a generator, so we have just one sine wave. But with three-phase electricity, we have a connection to each of the three phases. The phases are coils of wire which are inserted into the generator 120 degrees apart from the previous. This means the coils experience the peak of the rotating magnetic field at different times. And it's this that gives us our three phases, each with a different sine wave that is slightly out of sync from the previous. Remember, electricity wants to get back to its source in a complete circuit. As the current is flowing forwards and backwards at different times in each of the phases, we can essentially connect the phases together and the current will move between the different phases as the polarity of each phase moves forwards and backwards at different times. Any excess will flow in the neutral back to the source if needed, but that's only if the load on any of the phases is unbalanced. With single phase, we have these large gaps between the peaks, but with three phase, these can be combined to fill in the gaps and therefore deliver more power. Larger applications require a three-phase inverter, for example, to run the compressors in a large cooling system. The DC supply in this case will be a rectified three-phase AC supply. That means the three AC sine waves are combined together and pass through some diodes which prevent the electrons from flowing backwards. This turns it into a rippled DC waveform. We then use a capacitor to smooth the ripple out into a constant DC supply. Now we have covered this in great detail previously. Do check that out, links down below. To turn the clean DC into three-phase AC, we use a three-phase inverter. For this, we use 6 IGBTs. Again, I'll animate these as simple switches for simplicity, and I'll also number these as follows. To get our three phases, we need to open and close switches in pairs to direct the flow of current, form our supply and return paths. That way, the connected motor will experience alternating current. For the three-phase supply, we time the switches to simulate the three phases. Let's see how this works. First, we close switches 1 and 6. This will give us phase 1 to phase 2. Then we close switches 1 and 2. This will give us phase 1 to phase 3. Then we close switches 3 and 2. This will give us phase 2 and phase 3. Then we close switches 3 and 4. This will give us phase 2 and phase 1. Then we close switches 5 and 4. This will give us phase 3 and phase 1. Then we close switches 5 and 6, and this will give us phase 3 and phase 2. This cycle repeats again and again like so. If we check this with an oscilloscope, We now have a wave pattern that looks something like AC, except it's still a little bit square. This will work fine for some applications, but not all. So again, we need to use pulse width modulation to create the sine wave. So we're going to use a controller to rapidly open and close the switches to vary the output frequency and voltage, and that way we get our three-phase AC supply. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, LinkedIn, Instagram, as well as engineeringmindset.com.
Thank you so much. That's it for today's class. I will